Hello everyone. In this video we're going to learn how to solve equations containing rational expressions. We're also going to take a look at graphs of rational functions. Now we've previously seen equations containing regular fractions which don't have any variables in the denominator, and we know how to handle those. Basically, the most efficient approach would be to find the least common denominator for all the fractions that we observe in the equation. And then in this case, for example, the denominators are 2, 3, and 5, so they're all prime numbers. The LCD would just be their product, which would be 2 times 3 is 6 times 5 is 30. So we go ahead and take that 30 and we multiply it on both sides of this equation. Of course, whenever we multiply one side of an equation by a number, we have to do exactly the same to the other side to keep the balance of the equation. And now we go ahead and distribute the 30 on the side which has more than one term. So we get 30 times 1/2 x plus 30 times 1/3 equals 30 times 1/5. The beauty of the LCD is that, of course, it's the smallest number that all the denominators go into. So all the denominators are going to go into it and give us a whole number. So for example, 2 goes into 30 15 times. So we get 15x. 3 goes into 30 10 times, and 5 goes into 30 6 times. So then we get this really nice simple version of the original equation. It's equivalent to it, and what that means is they have the same solutions. Let me demonstrate that for you through a very simple example. Consider x plus 2 equals 5. Now that's a super simple equation. We all know what the solution is. We know that it's 3 without even solving it, right? We can just guess it. Oh, 2 plus what is 5, right? We know it's 3. Or we can just solve it officially by subtracting 2 from both sides, etc. Now consider multiplying both sides of that equation by a constant, say 4. So let's say we multiply both sides by 4. Let's see what happens. So we get 4x plus 8 equals 20. So we keep the 4x here, move the 8 over, so we get 20 minus 8. We just subtract 8 from both sides. So we get 4x equals 12. Divide both sides by 4. So we get x equals 3. Notice, same solution. So when we say this equation and this simpler looking equation with no fractions are equivalent, we mean they have a similar relationship to x plus 2 equals 5 and 4x plus 8 equals 20. Because this one is just a multiple of that one, they're going to have the same solutions. Multiplying both sides of an equation by a constant does not affect the solutions of the equation. So here, multiplying both sides of this equation by 30 is not going to have any effect on the solution of this original equation. So if this equation and this equation have the same solutions, wouldn't it be a lot nicer to solve this simple version? That's exactly what we do. So we end up with 15x equals 6 minus 10. 15x equals -4, so x equals -4 over 15. Could you have solved it by just dealing with fractions? Of course you could have. You would have just kept the 1/2 x on the left side, and you would have moved the 1/5 minus 1/3. You would have moved the 1/3 to the right side to get that. Then you could go ahead and divide both sides by 1/2. You end up with this, and then you can just simplify that, and you'll eventually end up with this anyway, with -4 over 15. Just to demonstrate, notice we had a nice trick for this. Is a complex fraction, and this has the numerator has more than one term. So if we take 30 and multiply it on the top and bottom, like this. And of course, on the top, we're going to distribute, so it's going to get multiplied by each of those terms. Notice we end up with 6 minus 10 over 15, which is, of course, none other than negative 4 over 15. So could you have worked with the fractions? You could have. And you know, if you're comfortable enough with fractions, this may be quicker. But most people, myself included, prefer clearing the fractions and then solving the simpler equations, if for no other reasons that this actually reduces the chances of making careless errors. So this is definitely the recommended method. If you have a particular relationship with fractions and you really love them, you could solve them just in fractional mode, but this is the method of choice. Now, we're going to handle equations containing rational expressions, which, remember, they're just fractions, but they happen to have variables in them, right? We're going to use the same techniques, but there's going to be one extra caution that we have to deal with, one extra step, and that is, you know, these equations that contain rational expressions, they may contain, as we've already seen, variable expressions in their denominators. That means we need to start by finding out what values of the variable makes any of those expressions in any of those denominators 0, and then exclude them from the set which would contain the solutions. So we'll see that in action in a minute. It'll make a lot of sense. Essentially, these are going to be the steps that are going to be involved in solving equations containing rational expressions. We're going to basically, first of all, factor all the denominators that we see. That's because that's going to help us find the two important things we need to find in order to solve such equations. One is the factorization will help us find the restricted values of the variable very quickly that would make any of the denominators 0. It'll also help us find the LCD of all the fractions in the equation. Once we have established the restricted values and the LCD, we'll go ahead and multiply the LCD on both sides, very similar to what we just did with 30 in the previous screen. And we're of course going to end up with that nice simpler equation that's not going to contain any fractions. Then we're going to just solve that simplified equation and find the solution candidates. Now, we don't say solutions because, remember, each of them needs to be checked against the restrictions that we found, the values of the variable that would make any of the denominators in the original equation 0. And then we're going to, once we have, you know, vetted the solution candidates and found the real ones that work, we're going to write the solution set. So let's see it in action. So here's a simple example. Remember, we're going to first try to factor any denominators. Now, these are already simple factor denominators. We don't need to do anything there. So we're ready to go ahead and state the restrictions of this problem, the restricted values of x. And we're also going to find the LCD of all the fractions that we see. So for the restricted values, remember, the only value of x that's going to make any of these denominators 0 is x equals 0 itself, right? This is a very simple case. So there's the restricted value of x. Now, basically, what you're saying is that x equals 0 can't be a solution. So x equals 0 can't be a solution. Why? Because when you plug it in, it makes terms in the equation undefined, and of course when terms of an equation become undefined, the equation itself becomes nonsense. So we can't accept that as a solution. Now we can also find the LCD very quickly. Notice For the LCD, we multiply the highest power of all factors, right? If everything is in prime factored form, which these are. So the highest power of 3 is just 3, and the highest power of x is just x that we see in any denominator. So the LCD is going to be 3x. So now we're just going to take the original equation, we're going to write it out, and we're going to multiply both sides by the LCD that we just found, by 3x. Now remember, on this side, the 3x is being multiplied by more than one term, so it has to be distributed, right? So instead of writing parentheses and then doing it in another step, let's save a step and let's just go ahead and distribute. So we get 3x times 1 over x plus 2/3 times 3x equals 3 over x times 3x. Notice we multiplied the 3x by each of the 3 original terms. And that's because of distribution on the left side. Otherwise, we're only multiplying 3x once on the left side, once on the right side. But on the left side, we have to distribute. That's why you see it appear twice. It's not that we're multiplying it twice, it's that we're multiplying it by more than one term, so it has to be distributed. So now, we carefully cross-cancel. We notice this x cancels that x, this 3 cancels that 3, and also this x cancels that x. So make sure it doesn't look like it's covering the 3. So all right, so carefully we write down what's left, the simplified version of the equation. So we notice that we get 3 plus 2x equals 9. See, 3 times 1 is just 3, 2 times x is 2x, 3 times 3 is 9. Everything else has canceled out. So we end up with 2x equals 9 minus 3, or 2x equals 6, so x equals 3. Alright, now that we have found x, we're going to do a restriction check, right? Remember, the only value that we cannot accept as a solution is 0. Is 3 0? No, it's not. So that means 3 passes the restriction check, right? Now, of course, remember, this is not a complete check. If you have extra time, you should check as you would check any other solution. You plug it into the original equation and see if it makes the original equation true. But the very least amount of checking you need to do with such problems, because that kind of check is usually optional, but this is mandatory. This check here, the restriction check, is not optional, it's mandatory, and you have to make sure that this number is not one of the values that causes problems for the equation. So once you've checked it and it passes, you go ahead and write your solution set. Again, if this is a test day and you have extra time left toward the end, it always benefits you to go ahead and actually perform a full check. So for a full check, we'll go ahead and substitute 3 for x in the original equation right here. So we get 1/3 plus 2/3, and we want to know if that's equal to 3/3. Of course, on the left we have two like fractions with the same denominator, so we can just keep the denominator and combine the numerator. So we're trying to see if 1 plus 2 over 3 equals 3 over 3. Well, 1 plus 2 is 3, so we get 3 over 3 equals 3 over 3. That, of course, is an identity, which means the solution is a valid one. Or in other words, 3 is indeed a solution. Again, this full check, oftentimes, once the first few problems have passed, the math books usually make you check on the first few problems, and then after that they leave it optional, up to you. But this check here, for this kind of problem, an equation that contains rational expressions, remember, is mandatory. These are mandatory check problems in the sense that you have to at least do the restriction check. And then you should be fine. Then write your solution set. All right. Make sure you can handle that on your own before we move on. Here we have another problem. It looks a little bit more involved, but nothing changes in the types of things we're going to do. So here the denominators are more complex, so we can factor them. So that's exactly the first thing we'll do. We'll go ahead and factor all the denominators since they're factorable and see where that takes us. So we end up with 4 over x plus 3 times x minus 2 equals, if you know how to factor these, go ahead and continue on your own. Pause the video and come back. That's how you really, really improve in mathematics. When you push yourself, watching mathematics get done by others only goes so far. All right, so 1 over x plus 2 times x minus 2. All right, so we have the denominators all factored out. Notice in this form, it becomes really simple to determine the values of x that make any of the denominators 0. We notice that, for example, -3 would make this factor 0, which means it would make this whole denominator 0 because 0 times whatever is 0. So we don't want -3, we don't want 2. 2 would do the same thing. It would make this factor 0, which of course would make the whole denominator 0 because that would be 0 times 5, which is 0, right? So we don't want, so let's write the restrictions up here. The restricted values, x equals -3, 2, and also, excuse me, and also -2, because that would make this factor 0, which would make this denominator 0 as well as that, right? So -3, 2, and -2 can't be solutions. And the LCD is also easy to find at this point. Notice the LCD is going to be the product of the highest power of each factor. So we notice for x plus 3, the highest power is 1, right? Both of these are first power. X minus 2 appears twice. Highest power in either one is 1. And x plus 2 occurs once, and it has a highest power of 1. So we're going to have one factor of x plus 3, one factor of x minus 2, and one factor of x plus 2 in our LCD. Quantity x plus 3 times quantity x plus 2 times quantity x minus 2. Okay, so that's our LCD. So we're going to go ahead and multiply it on both sides. And remember, because the right side has more than one term, when you multiply the LCD by it, it has to be distributed. So we're going to see it basically multiplied by each of the 3 terms that we see because of the distribution. So we end up with 4 times x plus 3 times x plus 2. Let me go ahead and put the x minus 2 on this side. Makes no difference. I'll move this 2 a little bit to the left to give us some room. Remember, we're going to multiply that by the LCD as well. So x plus 3 times x plus 2 times x minus 2. I'll move the 1 as well to give us more room. And once again, we're going to multiply the LCD. All right, now we go through and we cross cancel as much as we can. So here on the first term, we notice x plus 3 cancels x plus 3, x minus 2 cancels x minus 2. All right, now on the second term on the right side, well, the first term on the right side, we notice that we can cancel the x plus 3's and the x plus 2's. And on the final term, we can see that we can cancel the x plus 2's and the x minus 2's. Those are binomial factors. They're perfectly legal to cross-cancel because they are factors. We just simply cannot... Sorry, these whiteboards have a mind of their own, not as cooperative as the ones on my actual class boards. All right, classrooms. Okay, so we can cancel the x minus 2's. Have to be very careful at these edges. All right, now we go ahead and write down what's left. So we notice here we have 4 times x plus 2 equals 2 times x minus 2 plus 1 times x plus 3, which is just x plus 3, right? Okay, so we go ahead and we multiply it out and simplify, so we get 4x plus 8 equals 2x minus 4 plus x plus 3. So we have 4x plus 8 equals 3x minus 1. So in all equations that we solve, we simplify both sides before we move any terms around, right? So we're there now. Both sides are fully simplified. This is a simple linear equation. The approach for solving it is different from higher order equations. Now we take all the variable terms to one side, constants to the other side. So we get 4x minus 3x equals -1 minus 8. So we have x equals -9. Remember the mandatory restriction check. We want to make sure that, remember, these are the values of x that can't be solutions: -3, 2, and -2. So when we put -9 through the restriction check, how does it do in your opinion? You see, it passes because it's not one of those numbers. So passes. Again, whenever you have time, plug it in, do a full check. I'll leave that for you, otherwise our video will be even longer than it's already going to be. So we have solution set, which we will state as the set containing -9. All right, so make sure you can do that problem on your own before we proceed. That means writing it down on a blank piece of paper and just not peeking at all, doing it entirely on your own. All right, so here we have another one of these problems. You should definitely be able to do this on your own. So go ahead and give it a run and then, unpause the video. So go ahead and hit pause and try this on your own. It'll do you a lot of good to try to get it on your own efforts. Okay, so I'll come back. Remember, the first thing we're going to do is go ahead and factor all denominators. So the first one is a difference of squares. We know it factors as y plus 3 times y minus 3. The first one on the right side is already simple. So is the second one. So those we just write as they are. All right, now that all denominators have been factored, we can easily find the restricted values of y. Notice that y should not be either -3 or 3, because that would make at least one of these denominators a 0. So for the restricted values, we have y equals -3 and 3 that can't be solutions. For the LCD, we can see that we need to multiply the highest power of the y plus 3 factor by the highest power of the y minus 3 factor, and in both cases the highest power is just 1, so the LCD is going to be y plus 3 times y minus 3. If you happen to have, say, for example, a y plus 3 squared in one of the factorizations, then you would obviously use y plus 3 squared here. But we don't have that here, so all the binomial factors have a power of 1, so that's our LCD. So now we're going to multiply that LCD on both sides of this equation. This obviously has to do with the multiplication property of equality, which says if A equals B, that implies A times C equals B times C. So we're just using this property. We're just multiplying C on both sides of an equation. So here, our C happens to be the LCD here. So we're going to multiply this on both sides. And remember, this side, you have more than one term, so that is going to get distributed. So in the end, each of these terms is going to get multiplied by that LCD. So on the left side, we have 6 times y plus 3 times y minus 3. This is a completely new use for LCD. This is not using the LCD to combine fractions. This is using the LCD to clear fractions. And remember, you can only do this when you have an equation. You cannot do this if you're dealing with a rational expression alone, because there's no justification, there's no two sides, and no justification of multiplying both sides by any given LCD. An expression, by definition, only has one side, right? So on the right side of the equation, we do the same thing. We multiply the LCD by each term. Like so. Now we'll go ahead and cross cancel as much as possible. We notice that y plus 3 cancels y plus 3, y minus 3 cancels y minus 3. On the right side, y plus 3 cancels y plus 3, and y minus 3 cancels y minus 3. So the simplified version of our equation becomes 6 equals 1 times y minus 3, which is just y minus 3, plus 1 times y plus 3, which is simply y plus 3. Now, if this were a minus, we would have to leave parentheses so we could distribute. But since it's plus, we can go ahead and do without parentheses. So we notice that those two cancel out right away. So basically we have 6 equals 2y. Divide both sides by 2. We end up with 3 equals y. So we have a solution candidate, which means it needs to be run through the restriction check. Remember, the restricted values of y, -3 and 3 cannot be solutions. So look, we only have one solution candidate, and that solution candidate can't be a solution. It fails the restriction check. So that means, how many solutions does this equation have? Did you say none? You would be correct, okay? So here we'll say the solution set is empty. Because remember, there was only one solution candidate, and that one we can't use. So therefore, we have no solution. So we put solution set equals empty. Now this, if you've never seen, is called it's the symbol for the empty set. Some people call it the null set. Same thing. It's neither a 0 nor is it an O. It's like a circular object with a slash through it, just like that, /. Now, this notation there means one of those two things. Now, could you write it using regular brace symbology? Yes, you could. You would use the braces and just don't put anything in the middle. These two have the same meaning. Just don't mix the symbols. Don't put this in the middle of this or anything like that. Either use this. This itself means that. So it has the braces contained in its meaning. So either use this notation or use that notation. Or simply say the solution set is empty. So you say no solution. But if somebody asks you what is the number of solutions, what are you going to say? Yes, 0. The number of solutions is 0. So you can say no solution, or you can say the number of solutions is 0. So this problem should really highlight the importance of the restriction check while you do this type of problem. Just because you have an equation, it doesn't mean that equation is always going to have a solution. Of course, that's not limited to rational equations. Even if we were dealing with simple linear equations, not every equation had a solution. For example, if I give you the simple equation x equals x plus 1, you can try to solve that from now till the end of time. You're not going to find any solution because there is no number that stays the same if you add 1 to it. So if you try to solve this using the techniques you know, you just move the x's to one side like that, you end up with 0 equals 1, you end up with a contradiction. So a solution not having an equation not having a solution is not something that's restricted to just these more complex looking rational expression type of equations containing rational expressions. It can be it can happen to simple linear equations as well. Here's another one, very similar. You should definitely try it before you rejoin the video. All right, so as always, we're going to factor any denominator that needs factoring. We can see the first one sure does. That's a difference of square. It's going to factor as u plus 4 times u minus 4 equals, on the right side, those denominators are simple. There's no factoring possible, so we'll just rewrite them. Now, the restricted values, notice that there are only two values of u that would make any of these three denominators 0, namely u equals -4, that would make this factor 0, and this factor, and u equals 4, that makes this factor 0, and that factor 0. So we can see that those are the values of u that we need to stay away from as far as solutions are concerned. So u equals -4 and 4 can't be solutions. Okay, now we want to find the LCD, and for that we're going to take the highest power of u plus 4 and the highest power of u minus 4, both of which appear to be 1. So the LCD is going to be quantity u plus 4 times quantity u minus 4. So now we take that LCD, we multiply it on both sides, and remember on the right side there are two terms, so it needs to get distributed. So we're going to get this multiplied on each of the terms that we see. by each of the terms that we see. So u plus 4 times u minus 4. On the right side, let me move the 1 and the u a little bit to give us some space. So we're going to multiply the u plus 4 times u minus 4 by each of these terms. All right. So this one just doesn't want to cooperate. We'll just redo it. So now we cross cancel as much as we can. We can see that those two cancel out, so do those two. In the next term, u plus 4 cancels u plus 4, and finally u minus 4 cancels u minus 4. So we carefully write down what's left. So we only have 8 left on the left side. On the right side, we have negative times quantity u minus 4. Don't try to distribute, just write it. We'll do it in the next step. And then minus u times u plus 4. Those who try to do too many things in one step are the ones who get things wrong. All right. So we have 8 equals negative u plus 4 minus u squared minus 4u. So we have 8 equals, let's write the negative u squared first, that's the highest degree term, and then combine the negative u and minus 4u to get negative 5u, and then plus 4. So this is a quadratic equation, it's higher order, so we move everything to one side now that both sides are fully simplified, and get 0 on the other side. So let's move to the left side, so we get u squared minus, well, becomes plus, so plus 5u minus 4. We just moved these three terms to the left side, and of course they all change signs, because when you change sides you change signs because you're adding the opposite to both sides. And the 8 is already there, so that one remains positive because it doesn't move. And we have 0 left on the right side, so we get u squared plus 5u plus 4 equals 0. So we have u plus 4 times u plus 1 equals 0. Let's make sure this factorization is correct. First times first is first, last times last is last. Inner product plus outer product gives us the middle term, so it's correct. Now we apply the zero factor property. So we get u plus 4 equals 0, or u plus 1 equals 0. So this one will give us u equals negative 4, and the next one will give us u equals negative 1. So now we have to do the restriction check on each of these. So on negative 4, we see that it fails. It's one of those we cannot use as a solution. So this one fails. But negative 1, when we do the restriction check, passes. It's okay, because it's not one of these numbers. So this one passes. So we write the solution set to contain only negative 1. Again, you see how extremely important it is for you to do the restriction check, because otherwise, if you're like in a rush, you skip that, you would put both of those in, and of course that would be incorrect. Make sure you can handle this on your own before we proceed. In the next few examples, we're going to take a look at graphing rational functions. The first function we're going to look at is a famous one. It's called the reciprocal function for obvious reasons. And it's going to be the main function that we will study the graph of, and then we'll look at some transformations of that. In other words, we'll look at what happens or what needs to happen for this graph, for example, which is shown here, say to move to the right a certain number of units, or to the left a certain number of units, or up or down. We're going to learn how to do that very soon. So if we just go ahead and look at some values, we'll start with like -3. Notice that there's not a whole lot that's unusual anywhere other than really close to the problem point. What is the problem point? Well, remember, any value of x that would make this undefined is considered a problem point. And if you look at it, it's very simple. There's only one, and that's 0. So 0 right here is what we call a point of discontinuity, because notice it literally rips the graph up into two parts. There's what happens to the left of 0, and then there's what happens to the right of 0, and they're completely disjoint. They're separate pieces of this graph. So all the graphs we've seen for polynomials, etc., they've all been nice and connected, but this really gets split up at that point of discontinuity. Also, some really interesting stuff happens when the values of x get really close to 0, either from the left or from the right. So let's look at it approaching from the left. Notice when x is -3 right here, the y value is just -1/3. So that's -1/3 right there. So when it's -2, the y value is -0.5 right there. Each of these is half a unit, right? Those tick marks. When it's -1, you get -1. Now, as you start to get really close to 0, you see what happens. The values start to get really large, become really large negative values, right? So the way we explain this, because remember, if you have a numerator that is fixed, the smaller the denominator becomes, the larger the actual fraction becomes. And of course, if it's negative, it becomes a large negative number. Now, as you approach 0, we say the values of the function f of x, or the y values, approach -infinity. Notice when you're 1/1,000,000th of a way to the left of 0, that's so small we can't really graph it. But the y value has already hit -1,000,000, okay? So at 0, of course, the function f of x equals 1/x is undefined. In other words, f of 0 is 1/0, which is undefined. Then we start making the same journey slowly away from 0 toward positive values, right? Notice everything that we had here, which was negative, will have the same values but positive. So notice, as you get closer and closer to 0 from the right side, the values of the y, or the function values, approach positive infinity. We call the y-axis in this case the vertical asymptote for this graph. So what is an asymptote? It's a line or a curve that another graph becomes arbitrarily close to but never actually crosses. So in this case, we have two. We have the vertical asymptote, which is the y-axis, whose equation is, of course, x equals 0. And we have the horizontal asymptote right here, which is the x-axis. Now, in this way, too, notice as the values of x here get smaller and smaller, like -10, you get -0.1, etc. So the y values going this way become really small. Going towards 0, they become really large negative numbers. But when you approach this way, in other words, when the x values become smaller and smaller, or larger negative values, the y values get closer and closer to 0, but never actually become 0. So the x-axis plays the role of a horizontal asymptote. And of course, you know that the equation of the x-axis is just y equals 0. How about domain and range? Remember, domain is the set of all the acceptable x values, right? So if you look at all the x values that that can be used in this table, not that it is used, because remember, we skip a lot of values, don't we? We jump from -3 to -2, for example. Just between -3 and -2, there are infinitely many real numbers that we could have used in this table, right? So when we say the domain, that means all the numbers that are okay to substitute for x, right? And notice every real number is okay to substitute except that one problematic one, which is 0. Now, as far as the outputs also, notice that we seem to be getting all the y values possible except for what? The one y value right there, which is 0. So we say the domain is we can use the interval notation or the set builder notation. In interval notation, we say all numbers from -infinity to 0, stop there, don't include it. That's why we use parentheses. Union, that means put that together with all the real numbers greater than 0. So we show that by writing parentheses 0 comma infinity. By doing this, notice we've excluded 0 from the domain. To say it using set builder notation, we say it's the set of all real numbers x, that's x belonging to R is the set of real numbers, such that x does not equal to 0. That means all real numbers except 0. For the range, the interval notation will look the same, because you want all y values from -infinity to 0, and then from 0 to infinity. So it looks the same, but there's a subtle difference when you look at the set builder notation, because here these are y values, but there in the domain we're dealing with x values. So the only difference here is that we say all y belonging to R such that y does not equal to 0. So that's the graph of the reciprocal function. Now we want to look at some transformations we can perform on that function to move it one way or another. First, we'll look at horizontal translations of the graph of f of x equals 1 over x. So this is the one that's behaving as our reference function. So when we're going to say move something to the left or right, we're talking about moving this, the graph of this function. So we've put it here in the middle for reference, you see. That's the graph we just learned how to do in the previous screen. Now, if I change the input x to x minus 3, notice I'm actually going to move the problematic point, aren't I? Because when you have just 1 over x, the problematic point, which is the point of discontinuity, which splits it into two parts, is going to be 0. But when I look at 1 over x minus 3, 0 is no longer a problem. 1 over 0 minus 3, that's -1/3. Look, in the blue curve, 0, -1/3. That's a perfectly good point. The problematic point for 1 over x minus 3 is 3, because that's what makes this denominator 0. Just set the denominator equal to 0, and you get x equals what? In other words, if you just solve this simple equation, what do you get? You get x equals 3. So right there is where the new vertical asymptote is. And notice that as far as the domain and range, the range appears to be the same as it is for this one, right? The same y values are in play, but the domain changes because we're going to exclude this time not 0 but 3. So we remember the domain and range for f1. Here f1 of x is just our reciprocal function, so we know that that's from -infinity to 0 union 0 to infinity, and for the range we have the same But for F2, the blue graph, we know that the domain is going to change. We're going to have negative infinity to 3 union 3 to infinity. And for the range, of course, remember both of the blue curve and the green curve, which we'll discuss in a minute, have the same output zones, so the range is the same. Okay, for F3, notice this time we're changing the input x to x plus 3. So we're moving the problematic number, but notice what is the value of x that makes x plus 3 0? Exactly, negative 3. So this time the vertical asymptote has moved here. So the domain of F3, notice, is going to be negative infinity all the way up to negative 3 union negative 3 comma infinity. And for F2, the range of F3 is going to be the same as the other two functions. All right, so we recall that the blue dotted line or dashed line here has the equation x equals 3. That's the vertical asymptote for the function f2 of x equals 1 over x minus 3. And the green dashed line here has equation x equals negative 3. That's going to be the vertical asymptote for the green graph. Notice that if this red graph were made of, say, wire, right? What changing 1 over x to 1 over x minus 3 does is basically picking up the red graph and moving it 3 units to the right. That's why we call it a horizontal translation or shift, okay? And notice that what happens when you change 1 over x to 1 over x plus 3, it's like taking the red graph, both pieces of it, of course, and moving both pieces 3 units to the left, okay? And again, this would be considered a rightward horizontal translation. This is a leftward one. And we discussed the domain and range. So make sure you understand the difference here. It's subtle, important, and we're going to look at vertical translations now. All right, so notice if we start with f1 of x equals 1 over x, and we don't change the output 1 over x, but what we do, the input x remains the same, we'll bring some change at the output level. So we're going to actually take the entire output 1 over x and add 3 to it, or take away 3 from it. What that's going to do is it's going to take the original function f of x in red, f1 of x, that's just 1 over x, which we're familiar with now, and you can take it and move it 3 units up with this function, f2 of x equals 1 over x plus 3, and 3 units down. Notice no horizontal change because we're not changing the input. We're bringing a change at the entire output level by adding 3 to the output or subtracting 3 from the output. So notice that the vertical asymptote is the same for all 3 of these functions, and it's the y-axis, which is also known as x equals 0. Now, just as the blue graph with equation f, or with expression f of 2 of x equals 1 over x plus 3, was moved up 3 units, so did its asymptote. So the asymptote of the red graph, the original reference graph 1 over x, is the x-axis itself. You move it up 3 units and you get y equals 3. Remember, the equation of the x-axis itself is y equals 0. So the equation of this horizontal line is y equals 3. So this is the horizontal asymptote for the f2 of x, which is 1 over x plus 3. So, and the equation is y equals 3. Now, for the green graph, notice that's like taking the red graph and pulling it down 3 units. So the asymptote is going to pull down with it. So the asymptote also goes down 3 units, and it moves to this point, -3. So the equation of the horizontal asymptote for this one, the green graph, is going to be y equals -3. Again, both of those are called vertical translations. Notice that the domain for all of them is the same, because the same value of x makes all of them undefined, namely 0. So the domain for all of them is, let's go back to the other corner. Domain for all of them is -infinity to 0 union 0 to infinity. The interval notation is by far the most common notation as you move on in to higher math classes. So for the f2, same domain. Also for f3. The range, however, if you notice, changes. Notice that for the red graph never crosses the x-axis. But the blue graph never crosses this line. Remember? The line y equals 3. So that means it can obtain all y values except for that one y value. So for f1, which is the original red graph, we know that the domain is -infinity to 0 union 0 to infinity. But for f2, we know that it's going to be all y values except 3. So it's going to be -infinity to 3 union 3 to infinity. For f3, which is down here, notice this function only misses the y value here. It never crosses y equals -3. So the range will be all y values from -infinity to -3 union -3 to infinity. In case you're wondering what that looks like in set builder, that's all y in R such that y does not equal to -3. This for R2, for F2, that's all y in R such that y does not equal to 3. That's the set builder version. For F1, we've already seen it, all y in R such that y does not equal to 0, etc. Okay, so again, these are examples of vertical translations of this red function. Remember, it's always translations of some function, some reference function. In this case, our reference is f of x equals 1 over x. Here we're calling it f1 of x. All right, so make sure you understand those. Now, the beauty of these translations is that you can even do more than one type at a time. So for 1 minute, ignore the positive 5. Imagine you just had f of x equals 1 over x minus 4, right? You know what that would do. That would move the graph of f of x equals 1 over x 4 units to the right, right? Now, imagine you were just dealing with 1 over x plus 5. What would that do? That would move the graph 5 units up. So what does this function do to the graph of f of x equals 1 over x, it does both. It moves it 4 units to the right and then 5 units up. So in other words, the easiest way to do this is to start at 0, 0, go 4 units to the right, 5 units up, make yourself a new pair of axes. These would be called the translated axes. And then take the graph of the 1 over x function, which would have been right where I'm tracing, and move it over there. So one piece will go here, one piece will go to the left side of it here. So you can see both the horizontal and vertical asymptotes have moved. The vertical asymptote is this line. Remember, that's the point 4. So x equals 4 is the vertical asymptote. The horizontal asymptote is this line here going through 5. So that's y equals 5. And the domain of this function, remember, is going to include all x values except this one that makes it undefined. So all x except 4. So negative infinity to 4 union 4 to infinity. The range, of course, will be all y values, but it'll never cross this line, y equals 5. So all y values except 5 will be in the range. So negative infinity to 5 union 5 to infinity. So if you would like to see it in set builder notation, the domain is all x belonging to R, such that x does not equal to 4. The range is all y belonging to R, such that y does not equal to 5. There it is. So that's what we would consider to be mixed translations of the graph of y equals 1 over x, or the reciprocal function. So the last thing I wanted to tell you is that these translations that you just noticed us explain for the graphs of the reciprocal function f of x equals 1 over x, and you know, whether we shifted it to the right or left or up or down, aren't limited to just those functions. They work for any function. So I thought I would show you the generalized notion here. Notice that if you let's assume you know the graph of some function f of x, right? So that's given. Now if you want to obtain the graph of f of x minus 2, meaning replacing the input of that function with x minus 2 or x minus k in general, that would just move the graph, shift it k units to the right. Notice it's a little counterintuitive, because when you see minus you usually think left, but that's not the way it is when you're doing a shift to the right. So to obtain if you know the graph of f of x, you can get the graph of f of x minus k by moving the graph of f of x k units to the right. You can get the graph of f of x plus k, as long as of course k is positive, right? By moving the graph of f of x 2 units to the left, or in general k units. Here I'm just using a specific example to make it easier to see. So here we're using 2 for k, right? So these are horizontal translations. And vertical translations, let's say you know the graph of f of x again. To get the graph of this function, f of x plus k, you would just take the graph of f of x and move it k units up. If k is 2, for example, you move it 2 units up. To get the graph of f of x minus k, you take the graph of f of x, move it 2 units down. Again, those are called vertical translations. That should pretty much wrap it up for this relatively long video. Sometimes it cannot be helped, I'm sorry, but I hope you learned something, and Make sure you practice and stay safe until our next video.